Very good, thank you. And thanks to the organizing committee for inviting me to give you all an update on our two radio science payloads, ROLSES and LuSEE Nite, that are scheduled to fly on NASA's CLPS landers over the next few years. This first picture you see here is an artist concept of the Intuitive Machines 1 lander that Joel Kearns talked about a little bit, and you see two of the deployed monopole antennas, two of the four that will be part of the ROLSES mission. Next slide, Sam. So a little bit more on ROLSES. As you might expect, it is an acronym, and it has to do with the lunar surface photoelectron sheath, something that has not been measured before on the surface of the moon. And we're going to be using these low frequency deployable antennas, stator antennas, which are hollow tube antennas. And you see in the middle picture here, these are the actual flight models stowed. They pop open, they're spring loaded. These kind of antennas have been flown literally hundreds of times successfully in space. The brains of the instrument is our radio digital spectrometer board driven by an FPGA. This instrument is a new build, but it is based on some heritage from NASA's SMAP, Earth Remote Sensing Satellite. The team is based out of Goddard, who built the instrument. Nat Gopalswamy is currently the PI. Bill Farrell and myself are two of the lead scientists for this mission. Our radio spectrometer is going to operate over two bands ranging from 2 kilohertz all the way up to 30 megahertz. And as I mentioned before, we're scheduled to fly later this summer on the Intuitive Machines 1 Nova-C lander. Next slide, please. So our landing site you see here is on the edge of the Malapert A crater. We're about 10 degrees from the South Pole, from the Shackleton crater. This looks to be a good landing site. We had quite a bit of back and forth on selecting this landing site from what we were originally scheduled on the near side, but I think we've settled on a good location now. Next slide, please. So the science goals, as the name implies, we're going to be measuring this plasma that is expected to be this ionized plasma near the surface is the result of interaction between the solar wind and the regolith. Our antennas are distributed one pair 1 meter above the surface and the other 3 meters. So we can use the electron plasma radio frequency, which is expected to be below 1 megahertz, to then measure the plasma density. We're also going to be looking at detecting solar, planetary, and other radio emission and exploring the radio galaxy spectrum below 30 megahertz. Next spectrum, please. Next slide, please. So speaking of spectrum, this is what we expect our data to look like. These you're looking at here are actual data from the WAVES radio instrument on board the WIND spacecraft, which is located at Earth Sun L1. This is a dynamic spectrum, so we're looking at frequency on the y-axis versus time on the x-axis, 24 hours. And one of the things you can see immediately is how rich this low-frequency radio spectrum is. So this is either your friend, if you're interested in some of these activities, or it's your nemesis, as in the case of radio cosmology, that is a high background, one of the reasons we want to go to the far side of the moon for cosmology. But you see, for example, RFI, radio frequency interference, these horizontal lines, this is coming from the Earth's human-made interference. There's Jovian, strong Jovian bursts associated with the Jupiter Io coupling. There are solar bursts type 2 and type 3 solar bursts here shown mainly below a megahertz. And then there's also the Earth as a strong source of auroral kilometric radiation, AKR emission. This is major cyclotron emission created by high energy particles spiraling in the magnetic field of the Earth. So this is interesting because we can use this as a template of what we might expect exoplanets that have that have magnetospheres. And we hope to be able to use some of these data that we'll collect with ROLSES to extrapolate on what observations we would like to undertake of nearby exoplanets from a radio far side array. Next slide, please. This one will show you just some of the instrument parameters, but also of interest on the right-hand side are some recent pictures taken of the integration of the various payloads onto the panels will be bolted onto the side of the lander, including down in the lower left here is the, once again, the stator antennas. Finally, last slide for ROLSES at least is a couple of pictures that we took last year when I visited Intuitive Machines. And you can see a full-scale model of the lander and the two large propulsion tanks that are over here. And then on the right side with my colleague Susan Lederer is the NOVA Control Center built by Intuitive Machines. And as I mentioned before, right now, the schedule is to launch in the third quarter of this year. So let's move on to the next slide, if we could, Sam, and talk a little bit about the second manifested mission that Joel mentioned as well. And this is LuSEE, the Lunar Surface Electromagnetics Experiment at night. This will be the first 21 centimeter cosmology observations from the moon. It's going to the far side, and we're going to have batteries so that we can operate at night. Joel mentioned that Firefly Aerospace was recently selected as our lander, and you see an artist concept of that lander with our LuSEE Nite receiver box on top and the antennas. This is led by my colleague Stuart Bale, who's the PI, the NASA PI at Berkeley, and also Andrzej Slozar, who's the liaison with the Department of Energy, who shares some of the funding for this mission. Next slide. You'll see a little bit more here. First, I wanted to just mention why we're going to the far side, because it's enabling for low frequency radio astronomy cosmology. We've known this for many decades. It's uniquely radio quiet because the rock of the moon, the 2,500 kilometers rock, block out radio emission from the Earth. For all intents and purposes, it lacks a significant ionosphere for observations above a megahertz. And unlike the Earth, is a dry, stable environment, which is important again for very sensitive observations. Now, next slide, I'll tell you a little bit more about the instrument. Next slide, Sam. So here you can see a cartoon picture of the deployed antennas. These are 6-meter tip-to-tip cross dipole antennas. We're going to have this on a turntable. And the reason is we're going to also be launching along with LuSEE Nite a radio beacon that will be in lunar orbit that will allow us to map the antenna beam, which is very important. And Joel also mentioned that we'll be deploying a lunar Pathfinder comm satellite built by NASA. This instrument will have a band going from roughly 1 to at least 50 megahertz. And I mentioned the partnership already with DOE and the batteries. Very importantly, also is a philosophy of operations here, in which after the lander lands, it turns off and therefore minimizes the amount of electromagnetic interference, which we have carefully controlled with our instrument, because we will be controlling the comms and the operations. Next slide is just a little bit more about the instrument. Next slide, Sam. Again, showing the turntable, the instrument, the battery box. The large brown is the battery box, and then our white box to the right of it is the receiver. Also on the right-hand side of the slide is a system block diagram showing that what we're doing is a voltage measurement, but we'll be measuring all 4 of the Stokes parameters. So we'll be looking at polarization as well as total intensity information. Next slide, please. So what's the science we want to do? Well, the science is that LuSEE Nite is going to be the first radio cosmology pathfinder experiment from the moon. And this is responsive to the Astrophysics Decadal Survey that identified the dark ages of the early universe as the discovery area for cosmology. And you see in the lower frame here a cartoon picture of the evolution of the universe from the Big Bang on the left to today's universe on the right. And there's this large unexplored region of the early universe called the cosmic dark ages before the first stars and galaxies formed. So you can't sample it with James Webb or Hubble because there's no stars and galaxies, but this period is filled with neutral hydrogen. And the next slide will show you what the data will look like, and that is a spectrum. Next slide, please. The global spectrum of this spin flip transition, this hyperfine transition of neutral hydrogen that produces in the rest frame a 21 centimeter wavelength. By the time we receive it, redshift it out to 10 meters or more, frequencies below 100 megahertz. And below on the lower right is some models of the expected spectrum. This is brightness temperature measured against the background versus frequency. And what you see in all these models are two large absorption troughs, one in the dark ages, which is just a playground for testing fundamental models of physics and cosmology, things like dark matter and dark energy. And on the right-hand side, during the cosmic dawn, that trough for examining details of first stars and galaxies. So last slide is just a summary then that Joel implied, the CLIPS program is innovative, but it's high risk and high reward. But it opens up, regular access to the lunar surface for us all. ROLSES and then LuSEE Nite are going to take advantage of that. And these will be precursors to what we are planning for a future array of low frequency antennas on the lunar surface, possibly in conjunction with deployment with Artemis astronauts, as we described recently in another lunar surface science workshop. I'll stop there. Thank you.